Hello and welcome back to Calculus 2, section 9.2, properties of power series. So we talked about power series last time, and today we're going to take a look and finish the chapter on power series. We are going to look at properties. There are a few things that we can observe with power series. And the first concept that I would like to take a look is the interval and radius of convergence. It is very important for power series to converge because if they don't, they are useless. Power series approximate functions, and if we don't have this correspondence between functions and series, then we can't use them. So divergence means that summation adds up to infinity. Convergence means converges to a particular value. So if you look at this, I will take a look at the basic power series, which is x over 3 to the n, let's say. N starts at 0 and goes to infinity. We know it's a power series because it has x in there. And we know that this x can take on any value from negative infinity to positive infinity. I'm not restricting that. Now, you also see that this problem is actually geometric series. It becomes a geometric series as soon as you pick a value for x. Now you're allowed to pick anything, but careful. The value you pick will automatically set whether the power series converges or diverges. You know that the value, so in order for power series to converge, let's do it this way. In order for convergence, we have to have this x over 3 between, not including, negative 1 and 1. So I am allowed, if I solve this three-sided inequality, if I multiply through by 3, I get negative 3 less than x less than 3. So I'm allowed to pick any number, decimal. I can choose pi over 2, I can choose e, 1 over e. I can choose any number between these two values as x, and the power series up there will converge. So power series converges for all values between -3 and 3. So I can call this over here interval of convergence. So that's where we begin. So we understand that there is interval of convergence, and I hope you understand what the interval of convergence means. Now, any other value I pick, which is from negative infinity, including negative 3, union 3 to positive infinity, we are going to have divergence of this power series. So interval of convergence will give us the value, the x values, for which the power series will turn into a series which converges. So now we understand how to deal with power series, which is geometric ones. But what happens with other ones? Can we find it, right? And what's the radius of convergence? So there's a little bit more to discover in this case. So interval of convergence. Now, if you want to put this on a number line, which is the x number line, you will have to pick open circle 3 and open circle, sorry, negative 3 and 3, and you will have divergence, convergence, divergence, right? So depending on which values you're picking. We don't graph these things, it's just a visual representation for you to understand that if you pick a value between negative 3 and 3, the series is going to converge, and if you pick anything out of those bounds, it will diverge. So now that we are understanding this, I would like to work on the interval of convergence for general cases. So how do we find it at any time? So let's take a look at series 0 to infinity x to the k divided by k factorial. So which test should we use, could we use, to check for the convergence of this series? Well, we have a mix between the exponential and factorial. So which test are we using? Very good. By the way, over 700 people said ratio test at the same time, but just very far away, so stream didn't pick it up. So ratio test. We know that for ratio test, we are supposed to take the limit as k goes to infinity of absolute value x to the k times x when you peel one off, and then k plus 1. Let me do steps. Times this one flipped because it was supposed to be divided by it. Don't forget absolute values. Guys, if you forget absolute values, the problem will be wrong. So you must put these absolute values in. K goes to infinity. Now we're going to peel off one of the x's. We're going to peel off k plus 1 on the factorial. And then I'm going to cancel the x to the k's and k's factorial and get absolute value of x over k plus 1. Now, you have this limit to solve, and in the eyes of the limit, k is the variable we care about, which means x. X would be what? X would be the constant, technically, in the eyes of the limit. So I'm going to kick that x outside with absolute values attached to it, because I don't need absolute values for the remaining stuff, because k is always a positive value, so absolute values don't actually do anything there. We start k 0 and then, 1, 2, 3, 4. So I'm left with limit of k goes to infinity 1 over k plus 1, which is absolute value of x times 0, and that is equal to 0. Now that is always less than 1, and we know we have a convergence by ratio test. Well, it seems that whatever you pick as a finite number for this x, 0 will kill it, and 0 is always smaller than 1, which means that this is always convergent. So power series summation x to the k over k factorial converges for all x. That means that the interval of convergence is from negative infinity to infinity. You can also write it negative infinity less than x less than infinity if you want to, so one or the other. No, you don't have to write both. And the radius of convergence is also infinite. R equals infinity. That is the half of your interval, okay? So if you have on the number line, it's centered at 0, and you go to infinity on both ends, then the radius of convergence is just one side, and the interval of convergence is the whole thing. So this is your answer. In this case, power series converged for any x you pick. You pick negative 17, you pick positive 1000, pi squared, whatever you pick for x, that will be at the end multiplied by 0. Our calculations show that, and then it immediately becomes 0. 0 is always less than 1, so we know it's a condition of convergence, so this definitely converges. Let's take a look at the next example, even more interesting. 0 to infinity, negative 1 to the k, x minus 2 to the k, divided by 4 to the k. Great. Again, ratio test. So limit k goes to infinity. First of all, I can just erase this negative 1 to the k. I'm not even going to write it, because absolute value will kill it every time, right? So values of negative 1 to the k are either positive 1 or negative 1, and this is in absolute values, so regardless whether it's positive or negative, absolute value will always make it a positive 1, so it doesn't change anything. So I just ignore that piece. So I have x minus 2 to the k plus 1 divided by 4 to the k plus 1 times, and I'm flipping this one immediately, so I save a step. And then we do peeling. So peel off x minus 2. So that's that plus 1, right? You peel off. And in the denominator, peel off a 4 times, and we still have 4 to the k over x minus 2 to the k, and those will cancel. So 4 dies with this one dies with that one, and I have limit k goes to infinity, and what's left is the absolute value of x minus 2 in the numerator divided by 4 in the denominator. Observe that there are no k's, right? There are no k's. So this limit has nothing to do here. So we just forget about it. This is all we have as the answer, because there is nothing, the limit can't operate on any of these. So the value of that limit is 1 times this. Now, since we are looking for convergence, we set less than 1. So it is me who's going to come in here and put less than 1. Because a ratio test gives us convergence if the limit, answer for the limit is smaller than 1. So you will set that less than 1, and now you have this inequality to solve, which is absolute value x minus 2 over 4 less than 1. Remember that don't put less equal than 1 because for equal test is inconclusive, right? So don't do that. It's just less than 1. Now, if you know any algebra, you will immediately understand this way. You will multiply both sides by 4, and you will add 2 everywhere. This is how you find interval of convergence. You solve the limit, and once the limit is solved, you set that limit less than 1 because you are looking for convergence, and then solve the resulting inequality, which is giving us the interval. What this means is that any x you pick from this interval here, your power series on top will converge, and anything you pick outside of this interval, power series will diverge. So you are technically creating infinitely many problems, right? Because I can create problems for exams this way, right? I just write that formula with x, I solve the interval, and I say, okay, I want this problem to diverge, so I pick something outside of this unit. Great. I want the problem to converge, I replace x with a number from this range. All right, so now, what are other cool features? So we found this thing over here is the interval of convergence. Now I need a radius of convergence. Radius of convergence is the half of the interval. How wide is the interval? How wide is this interval? 8 units, right? You see that you have 2 units left of 0 and 6 units to the right of 0, so 2 plus 8 is 8 units wide. So radius of convergence better be 4, right? Because that's half of 8. You can, if you are confused with this, just draw. You draw the number line. You say this is my -2, 0, 2, 4, and 6. So now, from here to here, I have 8 units, which means the radius will be 4 units, so r equals 4. Interval of convergence, radius of convergence. Do you see something interesting here? Where is this radius starting? It's 2. Now look at your series on top, power series. That has to happen. This power series was centered at 2. Radius of convergence has to go left and right of it for the radius of convergence. So if you have just x, then it's centered at 0. And our previous problem was 0 and then infinities on both ends. Now it's centered at 2, and we have 4 units, so 2 plus 4 is 6, and 2 minus 4 is -2 for the radius of convergence. So now we've seen that we have the radius of convergence is 4. Previous problem was infinite. And then we also had the infinite interval of convergence last time. Now we have this finite convergence, interval of convergence. Note that -2 and 6 are not included in that convergence interval. One more example. Summation of k factorial times x to the k from 1 to infinity. Maybe I should leave you to enjoy this one for a bit. So try this one on your own.
It's divergent, right? Yes, that's what I thought.
I mean, I'm sure we'll find out. Oh, he's doing it now. That's cool.
I'm not related. I'm not related. I'm not related.
Is it possible to make this a 0? One x 0. Yep. So the only way to get this less than 1 is to get x to be 0. And in that case, the only one case, 1 point, 1 point. So if x equals to 0, we have convergence. Otherwise, diverges. So the interval of convergence is just 1 point, 0, and radius of convergence is just r equals to 0 because 1 point. So convergence at 1 point. Awesome. Yeah.
Did you just go to the beginning of the problem?
Yeah.
Do you have to do the ratio test, or can you just limit it down to divergence test?
Would divergent test show the point x equals 0? It wouldn't. It's always a ratio test. You always do ratio test. For all of these, you do the ratio test because ratio test allows you to set it less than 1, and then, I mean, you can do root test in some cases, but ratio test 95% of the time, 5% root test is best for convergence of power series. Right? With a smile. People pull off calculus. I can. I was waiting for math. Yeah, you can. Am I allowed?
Yes, we're about
So the last 2 lines are the answer.
how do you do the phone showing up? Is it not? It's becomes a collection. I don't know. It's not where it's lying. You can touch it. You can certainly. I know how to. There was some pull them down. So that's for the better grip, so it doesn't hurt it. Yeah, my brother got me 6 flags the other year. If you got it, 6 flags. Junior in high school. Good job. Grip on that. That one's starting. That one's a 3 millimeter. Oh, yeah. You gotta think like that. It's completely impractical.
Yeah. But there's some sequence. So power series can converge on the infinite interval, finite interval, or at 1 point. All of that is summarized in theorem 9.3 on page 678. Power series can converge on infinite interval, finite interval or at one point. Combining power series. So let's say, let power series ck x to the k converge to f of x, and power series dk x to the k converge to some g of x. On interval I. So let's say that's the setup. So number one, sum and difference. It says that summation of ck plus minus dk x to the k will converge to f of x plus minus g of x. That's the sum and difference. 2, multiplication by a power. So we are going to write that if you have x to the m in front of the power series ck x to the k, that can be imported inside and have it as x to the k plus m. We know the formula from algebra, right? When you multiply, when the base is the same, exponents add. Well, we use the property of peeling off, which is the backwards property. And then we have a composition. This is the nested, right? Like a function composition, which is, so h of x is given as b x to the m right, so you have that definition. Then, oh, this is if, sorry. Yeah, I'm gonna, oh, you're using pens? Look at this. Gone. Look now. Gone. If gone. If h of x is equal to bx to the m, and then you have m is a positive integer, b is a non-zero real number, then the power series, look, gone. So then the power series summation of ck of h of x to the k converges to f of h of x. Oh, this series, just gonna write it series. So how important could this be? Let me see by show of hands how many of you are planning on taking differential equations at some point in life. That will be everyone in this room. Now, I hope that when you take differential equations, you will look in all chapters, right? And then you're going to run into this. Right?
Jesus Christ.
So that's that. These rules that we just talked about, that's solving these equations, and there you go. You see how we combine the two power series? So in order for me to combine two power series, I have x to the n plus another series of x to the n, where the coefficient for the first power series plus the coefficient for the second. Here's my first plus second. X to the n is the one that is combined in the same series. And that gives you a recursion equation, and then you do differential equations after that. But that's that part. We also have, peeling the exponents. If you go back to power series, you first review power series, obviously. So all of this that we did in this class, there is a review for that. And then we talk about how to deal with derivatives. And shifting the counter is a very important part, so that we can go from the first derivative and shift the counter back in 0, so that we can line this series up. They have to start at the same number, they have to have the same exponent on the x, and so on. These rules and these properties play a key role in that course. So you have to play this game here in this chapter to learn it, not just to pass and then move along. So these rules will be used, and these are some of the basic rules that we have. And then differentiating and integrating power series. Differentiating and integrating power series is the next part, which is actually 9.4. Because they tell you that you differentiate power series term by term, or integrate power series term by term. So they gave you a definition here, or theorem, and then they put all of the problems in a separate section, 9.4. I don't know why. This is why and 9.3 is going to be Taylor series, which is actually defined in 9.1. So it's really weird why this has 4 sections. You should just have 2 sections. 9.1 and 9.3 combined into one section, and then 9.2 and 9.4 into one section, and be done. That's how Larson book does it. But anyway, such is the way. So let's define differentiating and integrating power series, PS.
Is this go chapter 9.2?
Yep. Do it term-wise. Done. Yeah, I'm done. This is nothing else to do. So you write out the series, and then and here example given in 9.4. Done. That's that part. Is there anything else that is interesting here? Nope, that's it. We're done. 9.2 done. Moving to 9.3. So we start the stream by stream.